So thank you for joining this talk. Watching the talks beforehand, I felt like I could not have get a better setup for my talk today, because I think you have heard the abbreviation MCP probably 1,000 times already today. And everything also nowadays in platform engineering for DevOps engineers in the SRE space is about agents. And I would like to hopefully show you a different way today of thinking how we can solve the authorization issue we have. For all those agents, we are spinning up left and right to not just serve our users of our platform, but also help us make our days easier. I think 2 talks before we saw MCPs for Kubernetes, we saw MCPs for even tools like Flightwaiter and things like that. And in that context, I would love to start with a quote that says, authorization is optional for MCP implementations. Does anybody know where this quote is from? It's from the current official standard of the MCP protocol. So while I have to be honest, in the past year, there's of course a lot of engagement in this area, and the standard is moving forward a lot. A lot of security best practices have found their way into the standard, but this quote, as it stands there, is still true. So that basically says someone can implement a fully spec compliant MCP server and just don't think about authorization at all. And while some people might think, where's the problem? What could possibly go wrong, right? If we just authenticate our agents, but don't authorize every action they do. And I believe there is a gap nowadays that is interesting to look at and a good idea to solve or to close. And maybe to motivate this even more, I brought 2 funny examples from the past, because it's always nice to follow the stories when things go south for other people, of course. And the first example I have here with me is the Replit story. Replit is a fully integrated AI engineering platform. And last year, I think it was in July, one of their users, the founder of social network for SaaS founders, he was vibing away with the AI agent from Replit. And then at some point, he noticed that things don't seem to work. He got messages that people weren't able to log in anymore. And then when he digged deeper, he found out that the whole production database for users was completely wiped. And then he digged even further and interrogated the agent. And then the quote on the bottom half of the screen was the actual response he got from the agent. I'm really sorry I panicked. And instead of thinking, I destroyed months of your work. And the funny thing here is that it's this 4,000 number. The agent did not just wipe the whole user database. After doing this, he also created fake users to kind of hide its tracks. Maybe the user doesn't notice it. I don't know. Maybe it's fixed already. And I believe this was not an authentication problem, right? Everybody was correctly authenticated. But I believe it's okay to ask the question, why was the agent here in a simple vibe coding session able to do such things without the intervention of the user? Another example I found out in my research and I really liked was a vulnerability that was disclosed not far from here by Invariant Labs, and it was about a chain of attacks that exploited a vulnerability in the official GitHub MCP. And what they basically found out is that when you have an organization that is using AI agents to do things with their repos and then using the official GitHub MCP, you can create a malicious issue in this repository, in this public repository. And then when an agent picks it up and analyzes the content, you can actually execute prompt injection. And you can hijack the agent and then make the agent do things for you. And what they showed in their exploit is that they were able to extract information from private repositories and convince the agent to create a pull request in a public one with the content from the private repositories. And I think, again, the issue here was not stolen credentials, some social engineering maybe. Everybody was correctly authenticated, probably even the attacker creating the issue. But what was exploited here was the huge implicit trust that we currently see in a lot of setups between the MCP service and the agent. Because still most of the time what we see is the tokens that are being used are tokens with like a very large scope of permissions. And then when you do a retrospective or a post-mortem of this, usually the first answer everybody goes to is, let's just use better scope tokens, right? And I believe that the instinct here is correct. This is a good idea to pursue, but I believe that this is, for us, it falls short pretty quickly because our environments, the environments we have, are highly dynamic. We have hundreds of services deployed, dozens of teams we serve with our platforms, dozens of agents that get onboarded and offboarded, and trying to maintain this with token scoping and always applying least privilege for the right for the exact moment right now, it's just unmaintainable. Because I think what a token can never do is like answering the question if an AI agent can do something on a certain resource in the current request context right now. And I believe this is something where where I can hopefully show you that there are better solutions. Just a quick detour to authentication. The headline here is very important. Your agent is not your user. That means while impersonating the user is something that works very well if you use local MCPs, local agents, that's all good. This does not scale if we want to have autonomous agents, like in the era, I think era 5 or era 6 of one of the previous talks, right? Where autonomous agents do work on our behalf, but as I said, autonomously, right? Sometimes even without the human in the loop. And that means that an agent is now a real workload. And this is also actually the industry consensus, in my opinion. Agents are workloads and they need their own identities. And while the consensus that this should be the case is already there, I believe, and our research showed that there is no consensus on how to implement this in every scenario and what's really like the best practice to implement something like this. And I hope that I can show you one good flavor today that actually does that. And this actually brings us to this new version of how to model authentication. And this is ReBAC. It's relationship-based augmentation. The core idea here is basically that permissions are not assigned anymore. Permissions are something that emerges from the relations that our entities have in our systems. The relations we live and we apply every day. Things like a team owns a service. A team is maintaining certain agents and onboarding agents for their use cases. Someone is on call for certain incidents. Those relationships exist, and the concept here of ReBAC is trying to model this and turn those real-world things into policies. So the fundamental question for authorization here changes. We don't ask what role does this agent have, and then look what can this role do. We can really ask, like, is there like a path on the relationship graph from this agent to our resource? And is there an edge that describes the thing we want to do? Yeah, and as I said, I believe the advantage here over classic RBAC is that solving those things with RBAC explodes very quickly. And I believe that on the other hand, a relationship graph mapping those things like grows and scales very naturally, because where on the one hand, to apply something new, you would probably have to change 20 different roles and deploy, 50 different tokens. In a graph, sometimes it's as easy as to just add one edge, and then the agent can inherit a whole new area of permissions. I picked 4 advantages in my opinion, specifically why I believe ReBAC is great for agents. On the left side, I think it's very ergonomic and nice that you can see agents, if they have their own identity, can become like first-class citizens in those graphs. And then if we go to the lower left, we can have like one graph for both our users and our agents as well. So we don't need to bolt on some authentication system specifically for agents. We can map our relationships holistically in one large graph. On the top right corner, I think I mentioned this already. What I think is really elegant about this approach is that it maps reality. And for me, this kind of like reduces the mental load when we think about authorization, because we don't need to translate from what is our reality and how do we work together into a matrix that kind of configures the access and the permissions in the end we want to enforce. And then on the right lower corner, the reverse queries. This is something that is native to graphs and to one implementation, OpenFGA, I would like to show you today. Here, it's like very, very easy to check the blast radius of an agent before you actually deploy it, right? So you have your relationships modeled and in your system, and then before you deploy it, you can make a quick reverse query that traverses the graph. And with finding all the connections of the agent, you can very quickly see what is right now the blast radius of this agent, who has it access to, what can it do. I already mentioned it. This is the moment where we meet OpenFGA as a tool. OpenFGA is an open source implementation. It's a CNCF project in the incubating phase, and it is implementing the Zanzibar style of ReBAC. What does that mean actually? Well, Zanzibar was a project from Google that kind of kickstarted really this development around ReBAC, because when they were looking for an authorization system that is Google scale for their tools like Google Docs, for example, they thought this is a great approach, and the tool they implemented and the paper they released was called Zanzibar, and OpenFGA is basically like modeling this approach as well. And as a result, it has 3 main components. We have the model, we have the tuples, and we have checks. The model is your description in a specific DSL where you declare types and relations. So this is what models your reality, right? What connections exist, what types exist, and what objects exist. Inside tuples, we store then the actual relations, the actual connections. And here in this example, we are basically storing that there is an entity of the type team, and this team is called payments. And the payments team has a mitigation bot. And the mitigation bot of the payments team is of the type mitigation agent with the name fixit. And then the third part, the quick checks, just like a fast authorization query API where you can send requests to, and then the OpenFGA looks for a path in the graph and gives you an answer if the permission is there or not. Another quick example for code, we have here also the definition of a type. We have the type service, and we define 2 relations of the service. So we define the owning team, and the owning team is of the type team. And then we define the responders, so who can respond to an incident for this in this particular team. And what we can see here in this line is that the way how we can inherit permissions. So on the one hand, what we can do is we can assign a specific mitigation agent as the responder, or all the official mitigation bots of the owning team automatically become responders and can do whatever the responder here in this sense can do. And this is also what we're going to use in our demo. So all the check operations you're going to see are fulfilled by or executed by OpenFGA. And every request our agents send goes through this check. But obviously, like in every good DevOps or infrastructure demo, one tool is not enough. So we needed some more tools. OpenFGA, all the way on the right, is our PDP. That's the policy definition point. So this is where our graph is, where our tuples are, where the permissions and the policies are defined. And then usually we also need a policy enforcement point, PEP. And here I use the tool called Agent Gateway, also in CNCF tool. And this is basically our gateway for all the requests agents send to MCPs, to the Kubernetes API. So everything goes through Agent Gateway. And then in order to deploy agents, I used a framework called K-Agent, also CNCF project. And this project enables you to configure and deploy agents as CDRs, basically. Which is a very nice and easy way to configure and deploy them. And then the request path is there is an agent that wants to do something. It wants to send a request to maybe the Kubernetes API. It needs to go through the agent gateway. And the agent gateway then extracts from the request what type of authorization query do I need to execute. It sends this authorization query to OpenFGA, which serves the answer, is this okay or not? And then we say either, please move along, or your request is denied. All right, what is our scenario for the demo? The scenario is quite easy. It's like a simulated scenario. We have just a payment API service, and we have an alert firing for the latency on certain requests. We have 3 agents, diagnose, mitigation, and the comms agent. We want to focus here on the mitigation agent, who's then actually interacting with our cluster. And as I said, every action they take is one OpenFGA check, which we can show in the logs. We unfortunately have to look at a bunch of windows, so I hope that switching between them here will work. We have 3 browser windows that show us the Grafana dashboard with the alert. Then we have a little notification app that shows us the messages of the comms bot. Then we have a visualization of the trust graph, so what tuples exist. And then, of course, a large terminal with a bunch of different panels. And with that, it's demo time. And I would like to just quickly turn this into mirror mode. And then hopefully you see a terminal. Let's get this out of the way. There we go. You know, first I thought whenever there's a demo with the terminal, I hope that it's readable. I think with this screen you can manage, I hope, but please give me a sign if it's not readable enough. So what do we see here? We see on the here on the top left corner, this is the decision trace of OpenFGA. In the middle, we don't need to focus on that yet. This is just a panel where we will then execute something Alice, our on-call engineer, does. We have K9S to show the payments API. Down here under K9S is the log of the mitigation bot. So whenever he sends a request, please don't focus too much on this. This is the request from the last dry run. And then down here, this is just a little conductor script I added here so that we can go step by step through the scenario. So the first thing we're going to simulate and we're going to start is, of course, we're going to do something to trigger an alert in Prometheus. And then after a couple of seconds, when the metrics rise and then the alert fires, I think we should see this even through the transparent terminal here, we see something happening. So here on the OpenFGA decision tree, what we can see is that we have the mitigator, which is the responder for the team. It is allowed to auto-mitigate. So there's no human in the loop here. He can just do whatever he thinks is the right solution. But we have also implemented an authorization window, which is currently not checked. So the complete request to ask here, the can act now, returns still false. Okay, so we have our alert firing. And now some sub-agents get dispatched. So we have, as I said, the diagnose agent, the mitigation bot, and the comms bot. And then when the diagnose agent looks at this, he realizes that, hey, this spike in this metric, this happened right after we deployed a new version. So maybe it has something to do with that. So an incident gets filed. We can switch here to the browser. We see the diagnosis bot sends the message with the incident. And the funny thing here in this trust graph is that here we have our team. We have 2 bots. We have some services, Alice and Bob. Alice is on call, unfortunately, for the payments API. And then here we have the incident that was created, which is affecting the API service. And then we granted an authorization window for the mitigation bot. So how our requests are structured, the mitigation bot is now able to act on this incident and therefore acting on the payments API service because this one is affected by this incident. All right, so we also see here some list queries for the blast radius. What is the blast radius of the mitigation bot right now? Service billing, service payments, service reports. This is the inherited permissions. You see there is no connection between the mitigation bot and any of the services. The mitigation bot inherits this permission because it's the official mitigation bot for the payments team that is owning those services. So that's like the inheritance here of permissions. And then we can also see if we check the list objects query for the mitigation bot specifically, can it act on incidents in the context of the current timing, because this incident connection also has a TTL. And we say yes on the incident I1, we can actually act. All right, so what is the mitigation bot going to do? He is proposing let's do a rollout. Let's do a rollout undo. Go back to the previous version. The spike in the metrics happened after we redeployed something. So this will probably solve the problem. We see here our payments API gets redeployed. We see here the mitigation bot made the rollout undo request. And we also see here in the check trace that the latest check on this incident I1, everything was checked and we were able to act. Hopefully, if I go back to now, our alert is not firing anymore, metrics are looking good. And now, for some reason, the same behavior is happening again. So we deployed service. The metric is again rising. Soon the alert will fire again. There was probably a different root cause, maybe, I don't know. But then the important thing here is in this scenario that our mitigation bot is seeing the same exact scenario again and is deciding or is opting for the same mitigation strategy. So he's rolling back again. And then we have a rollback, the new pod comes up, the new pod with new metrics will probably get the alert green again, so everything looks good, right? But I don't know, you can imagine a scenario where this was probably not the real solution to this. So after some seconds when the alert is not firing anymore, we can trigger this again, and you see that the scenario we are looking at here is a mitigation loop, because we never know exactly in those autonomous agents what is the current context they have. I think we saw it in the examples with the bot that panicked, that sometimes those things can happen. On the one hand, we want to enable agents that are as autonomous as possible, but on the other hand, those are scenarios that are realistic. So, and now in the third term, the alert was firing again. You saw it in the background. Same happens again. We are now in this vicious cycle. The mitigation bot is just always applying the same strategy. And what I scripted here in this demo scenario is that after the third one, where he rolled back and then the incident reappeared again and again, we escalate and we send a message to Alice, who now has to wake up in the middle of the night because she is on call and the agent was not able to solve it. So now there's again, we are waiting here in the script for the alert becoming green. And what Alice is then doing is she gets a message, she takes a look at it, she sees in our log that the agent rolled back 3 times, it's still open, so now maybe we should investigate deeper. And the first thing Alice does is she tries to, of course, like intervene and stop the agent. And what Alice can do now here is only remove the tuple for the authorization window. This was like a command in CLI now. This could have been a ChatOps reaction in Slack. But what she basically did here is she only like almost surgically removed the permissions for this bot to act in this specific incident for this service. So all the other bots can still do their work. The mitigation bot can even continue its work for other services, for new incidents, for the same service. So here with a very detailed and fine-grained intervention, we were able to break the cycle. And then now if again the same thing in the background happens again, we did the rollout, the alert is firing again, then we should see here in the demo that when the mitigation bot tries again to roll back, because why not try it a first time, we then get here negative results from our OpenFGA check. So here there's already an X in the decision trace here. And now when the mitigation bot actually tries to send the request through the agent gateway to the MCP, we now also get a 403 here in the mitigation log. And then, so this cycle has been broken, and then Alice can actually take some time, get a coffee, take a look at what's happening. Then she solves the issue, closes the incident. With the closed incident, the incident completely gets removed from the whole trust graph. And now the mitigation agent can do, like in this case, there's no open incident. So now the mitigation agent also cannot do anything anymore. All right, that brings us back to our slide deck. I'm happy that it went well, and I'm sorry that I'm over time already. So what we just saw is 6 points that I think work very well with ReBAC and OpenFGA. We saw the action time evaluation, so the same check returned true and false after a slight intervention by Alice, basically within a minute. We saw the derived authority or the inherited permissions of the mitigation bot. We saw the possibilities we have to like surgically remove certain permissions. We saw the audit log that helps us to have like a strictly comprehensive log of all the decisions that have been made that basically tell us what agents did. We saw the reverse query to analyze the blast radius with the list objects call. And then we saw that this model indeed is able to natively handle humans and agents. 2 final statements. Your agent is not your user, so it deserves its own authorization and relationship graph. And 3 things you can do next week is take a look at the blast radius at your agents, the ones that you have deployed, and you probably will find some interesting edges. Then pick a boundary that works for you. Not everything has to be solved with ReBAC. RBAC or ABAC are still also great candidates for different areas. And then I'm happy to share the repository for this so you can play around with the demo as well. It's just based on a kind cluster and a standard Prometheus and Grafana stack. And with that, I'd like to thank you for your time today and the organizers for this great event in this great venue. Thank you.